Take a black hole. Picture its surface. The boundary we call the event horizon, the edge past which nothing comes back. Now ask a strange question about it. How much information can that surface hold? Not the inside, the surface. The answer is a number that should not be possible. For a black hole whose horizon spans 1 square meter, the surface holds about 1.5 times 10 to the 69th bits of information. That is a 1 followed by 69 zeros. Let me put that number somewhere your body can feel it, because a number that large slides right past the mind. Humanity, across every hard drive and server and phone and data center ever built, has produced something on the order of a 1 followed by 24 zeros worth of bits. The surface of a single 1-meter black hole holds more than that. It holds unfathomably more. The gap between the two numbers is itself a number with more than 40 zeros in it. Every photograph, every song, every email, every film, every backup of every backup, the entire digital output of our species would not come close to filling the skin of one small black hole. And here is the part that broke the people who first worked it out. The information is not stored inside the black hole. It is stored on the area of its surface. Think about how wrong that should be. If you want to know how much you can fit in a box, you ask how big the box is on the inside. The volume. A bigger inside holds more. That is the most obvious rule in the world. But a black hole does not obey it. Double the radius of a black hole, and its capacity for information does not grow with the volume, the way the contents of a bigger box would. It grows with the surface, with the boundary, as if the inside were not where the storage happens at all. This is not a quirk of black holes. A physicist named Jacob Bekenstein worked out in the early 1970s that the rule is general. The most information you can pack into any region of space is fixed by the area of the boundary around that region, not the volume inside it. The boundary. We call that limit the Bekenstein bound, and we are going to come back to it many times tonight, because it is the first crack in something you have believed your entire life, without anyone ever telling you that you believed it. And once that crack opens, here is the question that comes through it. If the most you can ever fit into a region is set by its surface, not its inside, then what is the inside really? Could the three-dimensional world you live inside of, this room and the body lying in it, be nothing but a projection? The readout of information written on a flat surface you can never reach or see. If you find yourself drawn to questions like this one, subscribe to the channel and get comfortable. This is a long one, and it goes somewhere genuinely strange. The late physicist John Wheeler had a phrase for where all of this points. It from bit. The idea that the stuff of the world, the it, might be built out of information, the bit, underneath everything. That matter and space and you yourself might be, the deepest level, an arrangement of yes and no, of 1 and 0, written somewhere and read out as a world. That rule was discovered at the edge of a black hole. Then, over the decades that followed, a small number of physicists did something far more unsettling with it. They asked whether the same rule applies to everything. To the room you are lying in, to the space between you and the ceiling, to the whole universe. And when they ran the mathematics, it did not say no. It said that the three-dimensional world you feel yourself inside of might be the projection. It said The real description of you might be written on a surface you can never reach and never touch. We are going to walk all the way to that claim, slowly, and I am going to show you that this is not philosophy reaching for poetry, and not a guess that overreached. It is where the equations have been quietly pointing for 30 years. But to feel why it lands the way it does, you have to start with the picture it overturns. So start there. Start with the world the way you already know it. Here is the picture almost everyone carries, whether or not they have ever said it out loud. Space is three-dimensional. It has length, width, and depth, and those three directions are real and fundamental and simply there, the stage that everything else happens on. Inside that space, things have volume. You have volume. This room has volume, and volume is the container. Volume is where stuff goes. It follows so naturally that it barely feels like a claim, that the amount of stuff a region can hold scales with its volume. A bigger room holds more furniture. A bigger hard drive holds more files. A bigger glass holds more water. Make the container twice as wide in every direction, and you have not doubled what it holds. You have multiplied it by 8, because volume grows as the cube of size. This is arithmetic you learned without learning it. It is built into how you reach for a bigger bag when you have more to carry. Now push that intuition one level deeper, down to the question of information itself. How much detail does it take to describe what is inside a region? To specify it completely, down to the last particle? The answer, under the picture everyone carries, is also set by the volume. Because the stuff is spread throughout the volume, and every bit of stuff carries its own detail, its own position and motion and state. More volume, more places for things to be, more detail required to pin them all down. The information content of a region should grow with the space inside it. Of course it should. Where else would the information live, if not in the room where the things are? This is not a foolish idea. I want to be careful here, because it is easy to mock the old picture once you know how the story ends. The volume picture is not foolish. It is the considered conclusion of two completely separate fields of science, arrived at from two completely different directions, more than half a century apart. When two roads that start nowhere near each other end at the same door, you trust the door. That is exactly what happened here. The first road was thermodynamics, the science of heat. In the 1800s, as engineers built engines and tried to wring work out of steam, physicists developed a quantity called entropy. Loosely, entropy measures disorder, the amount of a system that is jumbled rather than ordered. A neat stack of papers has low entropy. The same papers thrown across a floor have high entropy. Heat flows, engines run, ice melts, and through all of it, entropy tends to increase. That tendency is the second law of thermodynamics, and it is about as close to an unbreakable rule as physics has. But what is entropy, really, underneath the talk of disorder? The man who answered that was an Austrian physicist named Ludwig Boltzmann, working at the University of Graz in 1877. Boltzmann saw that the disorder we measure on the outside is really a count of the arrangements we cannot see on the inside. A gas in a box looks the same from the outside, whether this particular molecule is on the left or the right. There are countless invisible arrangements of the molecules that all produce the same visible state. Entropy, Boltzmann said, is just the number of those hidden arrangements. The more ways the invisible parts can be shuffled without changing the visible whole, the higher the entropy. He wrote it as an equation so clean it is carved on his gravestone. Entropy equals a constant times the logarithm of the number of arrangements. That logarithm is the heart of it. It turns an unimaginable count of microscopic possibilities into a single tidy number you can measure with a thermometer. And notice what that count depends on. It depends on how many particles you have and how much room they have to be arranged in. It depends on the volume. Cram more molecules into more space, and the number of possible arrangements explodes, and the entropy climbs with it. To feel how fast that count explodes, forget gas for a moment and take an ordinary deck of cards. 52 cards. The number of different orders you can shuffle them into is about 8, followed by 67 zeros. That is not a typo, and it is not a metaphor. A single deck of playing cards has more possible orderings than almost any quantity you can name in the physical world. If every star in the observable universe had 1 trillion planets, and every planet held 1 trillion people, and every person shuffled 1 trillion decks, 1 trillion times every second, from the Big Bang until now, you still would not have seen them all. Not even a sliver of them. That is what a count of arrangements does. That is what entropy is really measuring. And for a box of gas, that count rides on the volume. There is a human detail here I cannot leave out, because the shape of it returns later tonight. The idea Boltzmann was defending, that heat is nothing more than the statistics of unseen atoms in motion, was not quietly accepted in his lifetime. It was fought. Some of the most powerful figures of his era, the physicist Ernst Mach among them, the chemist Wilhelm Ostwald among them, doubted that atoms were real at all. To them, atoms were a convenient fiction, a bookkeeping device, not actual things. Boltzmann insisted they were real, and that the visible world of heat and pressure and temperature was the large-scale shadow of their hidden motion. He did not live to see himself proven right. In September of 1906, in the seaside town of Duino on the Adriatic, Boltzmann died by his own hand after a long struggle with his health and his moods. The experiments that put the reality of atoms beyond any argument arrived only a few years later. Hold that pattern lightly in your mind. A man writes down a radical idea. The idea says the world we see is the surface expression of something hidden underneath it. His colleagues push back, and the confirmation lands just after the resistance, never before. We are going to watch that exact shape repeat itself 70 years on, around a young physicist named Bekenstein and a claim about the skin of a black hole. Set the sorrow aside, though, and keep the physics, because the physics is what held. Entropy is the count of hidden arrangements. The second law says that count only ever grows. Spilled milk does not climb back into the glass. Heat moves from hot to cold and never, on its own, the other way. The universe, left to itself, drifts from order toward disorder, from few arrangements toward many, and that drift is the most dependable direction in all of science. Break almost any other law, and a physicist will go looking for the loophole. Break the second law, and they will bet their career you made an arithmetic mistake. And every piece of that, the most trusted bookkeeping we have, was built on the quiet assumption that the arrangements being counted are spread through a volume. So thermodynamics handed down its verdict. The capacity of a region, its entropy, the size of its hidden possibility, grows with the space inside it, with the volume. That was Road 1, paved across the 19th century by people thinking about heat and steam and the limits of engines. The second road did not get built until the 20th century, and it started somewhere that had nothing to do with heat. It started with telephones. In 1948, an engineer and mathematician named Claude Shannon, working at Bell Labs, published a paper titled A Mathematical Theory of Communication. He was trying to answer a practical problem. How much can you send down a wire? How do you measure information itself so you can ask how much of it fits through a channel? How much survives noise? How much a message really contains once you strip away everything predictable? Shannon found the answer, and when he wrote down the quantity that measures information, it was the same quantity Boltzmann had written down for heat, the same logarithm of the number of possibilities. The mathematics was identical, so Shannon gave it the same name. He called it entropy. Information theory did not borrow the word as a loose analogy. It borrowed it because the equation was the same equation, doing the same job in a different costume. Entropy in a furnace and information in a telephone line turned out to be one idea. Hold on to what a bit actually is, because the whole night turns on it. A bit is the smallest possible piece of information. One yes or no. A single answer to a single either-or question. A coin that has landed, where you have not yet been told which way it fell. Heads or tails. Nothing smaller than that carries any meaning at all. And everything you have ever read, every photograph you have ever seen, every word in this sentence can be ground down into a long ribbon of those yes or no answers. The number of answers it takes is the amount of information. That is the bit. Shannon gave it its name and its mathematics, and in doing so, he turned information from a hazy notion into something you can count, like grams, like seconds. And underneath the engineering, here is what he found. Information is surprise. The predictable parts of a message carry almost nothing. If I tell you the sun rose this morning, I have given you no real information, because you already knew it would. The information lives entirely in what you could not have guessed. So a region of space thick with information is a region full of detail you would have to be told, particle by particle, arrangement by arrangement, because nothing about it could be predicted from outside. When a physicist asks how much information a region can hold, they are asking something precise and faintly unsettling. They are asking how much about that region is unknowable from a distance. How much has to be written down somewhere to make it exactly what it is and nothing else? And that is the convergence I want you to sit with, because it is the reason the old picture held for so long, and held so deservedly. Two fields, one born from steam engines, one born from signal wires. A century between them, neither one looking for the other. And they met on the same equation, the same logarithm, the same count of hidden arrangements. When that happens in science, you stop treating the conclusion as a guess. You treat it as bedrock. The information content of a region is its entropy. Its entropy is the count of its hidden arrangements. And that count, in every ordinary case anyone had ever examined, scales with the volume. Put the two roads together, and you get the consensus the whole of physics carried into the second half of the 20th century. To say how much can be inside a region, you measure the inside. The volume holds the stuff. The stuff carries the information. The information is the entropy. The entropy lives in the volume, length, width, depth, and everything packed into them. Solid, sensible, confirmed from two directions, and matching every experiment anyone had ever run. You could teach this. You could stand at a dinner party and explain it and be completely correct. by the standards of everything humanity knew, a bigger region holds more. The capacity is in the volume. There is no reason in the world to suspect otherwise. Except that there is one object in the universe where you can ask the question, how much can be inside this region? And the universe answers back with a number that has nothing to do with the volume at all. One place where you measure the inside, and the inside is not what sets the limit. One object where the entire careful tower I just built, 2 roads, 1 equation, a century of agreement, simply does not apply. And I do not mean it bends the rule, or stretches it, or asks for a small correction at the edges. I mean it throws the rule out. You can take the cleanest, most trusted result in all of thermodynamics, the one welded to information theory by 100 years of agreement, carry it to this single object and watch it come apart in your hands. The capacity is not in the volume. The volume might as well not be there. You already know what it is. We started there. It is the black hole. And for about 10 years after the first physicist noticed the problem, the rest of the field did not want to believe him, because believing him meant believing that the information was not in the volume. It was on the surface, on the boundary. And if that was true for a black hole, the obvious and frightening next question was whether it might be true for everything else. The man who first noticed the problem was named Jacob Bekenstein. In the early 1970s, he was a graduate student at Princeton, and his advisor was John Wheeler, the same physicist who gave us the phrase "it from bit," and who a few years earlier had popularized the very term black hole. Wheeler had a gift for asking questions that sounded almost like a child's and turned out to have no bottom. He handed one of them to Bekenstein, and neither of them could let it go. The question was about a cup of tea. A hot cup of tea has entropy. It holds heat. Its molecules jostle. There is an enormous count of hidden arrangements packed inside it, exactly the sort of thing the second law keeps its eye on. Now carry that cup to the edge of a black hole and let it fall in. The tea is gone. And here is where Wheeler slid the needle in. The entropy is gone with it. The disorder the tea carried has left the universe completely, dragged past a horizon from which nothing, not light, not information, not the faintest signal, ever comes back. That should be impossible. The second law does not let entropy simply vanish. It is the one rule in physics that only ever runs in a single direction, the rule physicists trust more than almost any other. And yet, a black hole, as everyone understood it then, was a perfect eraser. Whatever fell in got crushed down to 3 numbers, and 3 numbers only. Its total mass, its electric charge, its spin, everything else, every detail, every difference between a cup of tea and an encyclopedia of exactly the same weight was simply gone. The physicists of the day even had a phrase for that brutal simplicity, a phrase Wheeler himself loved. They said a black hole has no hair. Stop on that phrase, because it is carrying more than it looks. No hair. It means a black hole is the most featureless object that can possibly exist. Take 2 of them, built from wildly different things. One assembled from collapsed dead stars, the other from an unthinkable heap of old books and pianos and human beings. And as long as their mass and their charge and their spin happen to match, there is no measurement, none, not even one allowed in principle, that could ever tell the 2 apart. Every story that ever went in is erased down to 3 bare numbers. That total, ruthless forgetting is exactly what turned the vanishing cup of tea from a curiosity into a crisis. If a black hole truly forgets everything, then the universe has a shredder built into it, and the second law, with quantum mechanics standing behind it, was never, ever supposed to allow a shredder. So in principle, you could commit the perfect thermodynamic crime. Gather up all the disorder you ever wanted to be rid of, drop it past the horizon, and watch the entropy of the universe go quietly down. The accounting that the second law swore could never be cheated would be cheated, cleanly, with no body left behind. Wheeler is said to have enjoyed the mischief in it. Bekenstein could not live with it. His answer, when it came, was the kind of idea that gets a graduate student in trouble. If the entropy cannot vanish, Bekenstein said, then the black hole must be carrying it. The black hole itself must have entropy, and not a small amount. A black hole must hold more entropy than anything else of the same size anywhere in the universe. But that only sharpened the harder question. Entropy is a count of hidden arrangements. So what arrangements? A black hole was supposed to have no interior worth the name, no hair, nothing to shuffle around. Where would you even write the entropy down? Bekenstein looked for the one feature a black hole actually has that can grow and change, and he found his answer in the last place the old picture would have looked. Not the volume inside, the area of the horizon, the surface. He had noticed something peculiar and rigid about that surface. The horizon of a black hole never shrinks. Throw anything at all into it, and the area of the horizon grows. Crash two black holes together, and the single horizon left behind is larger than the two you started with, added together. The area only ever increases, which is, suspiciously, exactly the one-way behavior that entropy shows under the second law. Bekenstein made the leap. In 1972 and 1973, he proposed that the entropy of a black hole is proportional to the area of its event horizon. Sit with how strange that is against everything we built a moment ago. For a cup of tea, for a box of gas, for every ordinary thing in your life, entropy lives in the volume, in the room where the parts are kept. Make the thing twice as wide in every direction, and its capacity grows eightfold, with the cube, the way volume always does. But Bekenstein was saying that for the densest and most extreme object the universe can produce, the entropy ignores the volume entirely. It tracks the surface, the boundary, as if the black hole's whole hidden content were not buried inside it at all, but spread across its skin. Almost nobody believed him. And the reason was not stubbornness, which is the part that matters. It was a genuinely excellent objection, and it came from the sharpest possible source. If a black hole has entropy, then by the ironclad chain of thermodynamics, it must also have a temperature. And anything with a temperature radiates. It glows the way a hot iron glows, the way your own body glows in the infrared right now. But a black hole, by its very definition, was the one thing in the universe that could never let anything out. Nothing escapes, so it cannot radiate, so it cannot have a temperature, so it cannot have entropy. So Bekenstein, the argument concluded, was simply wrong. Hold on to the pattern I asked you to remember. A man writes down a radical idea, an idea that says the hidden content of the world is kept somewhere nobody thought to look. His colleagues push back, and they are not fools. They have real and serious reasons. The young Bekenstein in 1972 is standing almost exactly where Boltzmann stood a lifetime before him. The one mercy is that Bekenstein would not have to wait decades or die first to be proven right. His vindication came within 2 years, and it came from the very person best equipped to bury him. Stephen Hawking did not like Bekenstein's idea. He felt it leaned on his own work about horizon areas in a way that bent it out of shape, and he set out to settle the matter. So he did what a great physicist does when he wants to kill an idea cleanly. He took it seriously enough to calculate. He asked what genuinely happens to the quantum fields right at the lip of a black hole in the thin skin of space just outside the horizon, the one place where quantum mechanics and gravity are both forced to speak at once. What he found in 1974 was the opposite of what he went looking for. Black holes are not perfectly black after all. Empty space, it turns out, is never truly empty. Down at the smallest scales it churns, throwing up pairs of particles that flicker into being and annihilate almost at once, borrowed from nothing and paid back before the universe can notice. Right at the horizon, Hawking saw that bookkeeping can break. One particle of a pair falls in past the edge, while its partner escapes outward. To anyone watching from a distance, the black hole appears to be giving off a faint, steady haze of particles. It radiates. It carries a temperature. And to pay for the particle that got away, the hole gives up a sliver of its own mass. Over spans of time longer than the mind can hold, it shrinks. It evaporates. We call it Hawking radiation, and it turned the whole argument inside out. Because if a black hole radiates, then it truly has a temperature. And if it has a temperature, then by the same thermodynamics everyone had trusted to refute Bekenstein, it must have entropy after all. Bekenstein was right. Hawking, having set out to demolish the idea, had instead handed it the proof it needed. And then he went further. He pinned down the exact number that Bekenstein could only estimate. The entropy of a black hole, Hawking showed, is precisely 1/4 of the area of its event horizon, measured in one specific and almost unimaginably small unit of area. We have called it the Bekenstein-Hawking entropy ever since. 2 names fused together by a disagreement that ended in agreement. But the way a black hole radiates is so strange it works as a clue all by itself. So let me linger on it for a moment. The temperature of Hawking radiation runs exactly backward from what your intuition expects. Smaller black holes are hotter. Bigger ones are colder. The more massive and imposing the black hole, the fainter and cooler its glow. Take a black hole the mass of our sun. Its temperature is about 60 billionths of 1 degree above absolute zero. Not 60 degrees. 60 billionths of a single degree. That is roughly 45 million times colder than the faint afterglow of the Big Bang that fills all of space. And that has a consequence that catches almost everyone off guard. A sun-mass black hole is so cold that it absorbs more warmth from that ancient background glow than it manages to radiate away. Which means every black hole in the sky tonight is not shrinking at all. It is slowly growing and growing colder as it grows, and it will not even begin to truly evaporate until the universe itself has cooled and emptied out, hundreds of billions of years from now, long after the last stars have gone dark. And when the evaporation finally does take over, it is the slowest process there is. A black hole the mass of the sun would take something like 10 to the 67th years to disappear completely. The universe is about 14 billion years old. 10 to the 67th years is that entire age, multiplied by itself, and then multiplied again by billions. Turn the rule the other way though, and it bares its teeth. A black hole the mass of a mountain, crushed down close to the size of a single proton, would not be cold at all. It would blaze at 100 million degrees and detonate in a burst of gamma rays in a fraction of a second. The very same equation that makes a giant black hole colder than empty space makes a tiny one burn hotter than the core of a star. For the black holes that actually exist out there, the glow is almost unimaginably faint. A sun-mass black hole radiates with a power of less than a 10 billionth of a 10 billionth of a watt, which is why, half a century after Hawking predicted it, we have still never caught a single, real black hole in the act of doing it. We believe in Hawking radiation not because anyone has seen it, but because the whole structure of physics falls apart if it is not there. That unit of area is the thing to slow down on, because it is where the idea stops being abstract and starts being almost physical. The smallest length that means anything in physics is the Planck length, about 1.5 times 10 to the negative 35 meters. That is so small, the word small barely applies. If you took a single atom and blew it up to the size of the entire observable universe, then the Planck length, magnified by that same staggering factor, would still be no larger than a grain of sand. Square that length and you get the Planck area, the smallest patch of surface that carries any meaning at all. Now picture the horizon of a black hole tiled completely in those patches, the way a bathroom floor is tiled in squares. Hawking's formula says the black hole's entire entropy, the full count of its hidden information, comes to 1 bit for every 4 of those tiles. Not stored in the volume, stored on the tiling, on the surface. The complete description of everything that ever fell into that black hole, every star it swallowed, every cloud of gas, every cup of tea, is written across its boundary, 1 bit at a time, on a grid of squares far smaller than anything you will ever see or touch. And the amount of information that surface can carry runs past the edge of comprehension. A black hole with a horizon just 1 centimeter across, the size of a marble, would hold an entropy of around 10 to the 66th bits. To set a number that large somewhere your body can stand, consider that the same amount of disorder lives in a cube of ordinary water, roughly 10 billion kilometers on each side. That is a block of water wider than the whole solar system, out past the orbit of Pluto, squeezed down onto the skin of a marble. Take instead a black hole the mass of our sun, and the figure climbs to about 10 to the 77th bits. There are only something like 10 to the 80th atoms in the entire observable universe. The surface of one single sun-mass black hole holds a number of bits within shouting distance of every atom that exists. Here, the word comes to the center, and it is the word the rest of the night turns on. The boundary. Not the inside of the black hole, which may not even be a place in any ordinary sense. The boundary, a 2-dimensional surface that holds the complete description of a 3-dimensional world that fell through it. Bekenstein had rescued the second law in the bargain, which is worth one more moment. His rule said, you must never count only the entropy of ordinary matter and never count only the area of black holes, but always add the two together. Drop your cup of tea past the horizon, and yes, the tea's entropy disappears, but the horizon swells by more than enough to cover the loss. The books always balance. He called it the generalized second law, and it is held against every test. The perfect crime turns out to be impossible. The universe keeps its accounts, it seems, on the surfaces of its black holes. And that should have been the tidy and satisfying end of it. a young physicist had a wild idea. The greatest cosmologist of the age tried to refute it and proved it instead. The most trusted law in science was saved by writing entropy onto a boundary. But the very same calculation that vindicated Bekenstein tore open a wound that has not closed in 50 years. Look once more at Hawking radiation. The glow leaking off the black hole is thermal. It is featureless. It depends only on the hole's mass, its charge, and its spin, those same three bald numbers, and on nothing else whatsoever. The radiation streaming away carries no fingerprint of what went in. A black hole that swallowed a great library and a black hole that swallowed an equal weight of burnt-out stars give off radiation that is exactly, identically the same. Now let the clock run. The hole radiates and slowly thins, and after a stretch of time so long it makes the present age of the universe look like a single heartbeat, it evaporates completely. It is simply gone, and the radiation it leaves behind carried no record of anything that ever fell inside. So where did the information go? This is the black hole information paradox, and it is not a puzzle anyone invented for fun. It is a head-on collision between the two deepest theories we own. Quantum mechanics has an iron commandment. Information is never destroyed. The present always holds, at least in principle, enough to rebuild the past in full. You can scramble information past any hope of practical recovery, but you can never truly erase it. And here is general relativity, describing an object that seems to erase it entirely, that takes a library and a heap of dead stars and grinds them both down into the same anonymous heat, and then vanishes, leaving nothing behind to tell them apart. One of those two theories has to be broken, or the information has to be hiding somewhere we have not thought to look. And the one hiding place that fit, the only one, was the boundary. The same surface that already, thanks to Bekenstein and Hawking, was carrying the entropy. Perhaps nothing that fell in was destroyed at the center. Perhaps it was smeared across the horizon instead, encoded onto that two-dimensional skin, waiting in some hopelessly scrambled form to leak slowly back out inside the radiation. Perhaps, for a black hole, the surface was simply the whole truth, and the interior was only a story the surface was telling. That was a strange enough thing to believe about black holes, but a small number of physicists looked straight at it and asked the question that should not have had an answer. If the complete description of a black hole's three-dimensional interior can be written on its two-dimensional boundary, then why should black holes be special at all? Why should the same rule not hold for any region of space whatsoever? Why not this room? Why not the entire universe? And when they tried to turn that reckless question into hard mathematics, they did not get gibberish back. They got the most cited idea in the history of modern theoretical physics. We are going to meet the three people who built it and find the exact and careful sense in which the world you are lying inside of tonight may be the projection, and the boundary may be the page it is printed from. The first of the three was a Dutch physicist named Gerard de Hooft, and he is not a man whose ideas you can wave away. A few years after the work I am about to describe, in 1999, he won the Nobel Prize in Physics for unrelated work that helped put the standard model of particle physics on solid ground. So when a future Nobel laureate looks at the black hole result and says, quietly, "I think this is telling us something about everything," the right response is to lean in. In 1993, 't Hooft wrote a short, strange, and now famous paper He titled it Dimensional Reduction in Quantum Gravity, and he dedicated it to his late mentor, the physicist Abdus Salam. In it, he said the reckless thing out loud. A black hole stores the full description of its three-dimensional contents on its two-dimensional surface. What if that is not a peculiarity of black holes? What if it is a law of nature, true of every region of space there is, including the one your body is occupying at this moment? He had an argument for it, and it is so clean, I want to walk you through it slowly, because once you see it, you cannot unsee it. Take any region of space you like. This room. Now try to cram information into it, more and more of it. Here is the catch that ordinary intuition forgets. Every bit of information you store has to ride on something physical, and everything physical carries energy. And energy, by Einstein, is a form of mass, and mass bends space and pulls on its surroundings. So as you pack more and more information into your region, you are also piling up more and more mass inside it. Keep going, and you reach a hard wall. Pack enough into the region and it collapses under its own gravity. It becomes a black hole. There is no avoiding it. Information is heavy, and too much of it in one place buckles space itself. And the instant your overstuffed region becomes a black hole, you already know the rule that takes over. Its information content is now set by the area of its fresh new horizon, not by the volume you were so busy trying to fill. Follow that to its conclusion. It means you can never pack more information into a region than the amount that would tip it into becoming a black hole, and that amount is fixed by the surface area of the region, never by the volume inside it. So the Bekenstein bound was never a quirk of black holes. It was the ceiling on everything. Every region of space that exists, your bedroom included, has a maximum possible information content written not through its interior but across its boundary. De Hooft gave the principle the name it still carries. He called it holographic after the hologram, and the name stuck because the name was right. The second of the three is an American physicist named Leonard Susskind, one of the founding figures of string theory and a man who has spent a long career cheerfully detonating other people's certainties. Susskind took 't Hooft's principle and gave it both a sharper mathematical spine and the image that named it for good. In 1995, he published a paper with a title that does not flinch: The World as a Hologram. Picture what an ordinary hologram actually is, because the comparison is exact, not poetic. A hologram is a flat piece of film, two-dimensional. There is no depth inside it, no interior, nothing behind the surface. But that flat film is etched with an impossibly fine pattern of light and dark, an interference pattern, and when you shine the right beam of light through it, a full three-dimensional image springs up into the air in front of you. You can move your head and see around the sides of the floating object. The depth looks completely real, and every last bit of that depth was encoded on a flat surface that has no depth of its own. Susskind's claim, written in cold mathematics rather than wonder, was that the universe is built the same way. The three-dimensional world, he argued, is the projected image. The genuine description, the actual stored data, lives on some distant two-dimensional surface, written at a density of about 1 bit for every Planck area. The exact same accounting, notice, that Bekenstein and Hawking had stumbled onto at the horizon of a black hole. The depth you see, the space you walk through, the gap between you and the far wall, would all be the convincing image thrown off by a flat page of information that you can never step around to glimpse the back of because you are part of the image on the front. Susskind did not arrive here gently, and the fight he had on the way matters. For the better part of 2 decades, he was at war with Stephen Hawking over precisely this question, whether a black hole destroys the information that falls in. Hawking, for years, said it does, and quantum mechanics will simply have to make its peace with the loss. Susskind found that intolerable, the same way Bekenstein could not stomach the vanishing tea, and he insisted the information had to survive somewhere, scrambled and smeared across the horizon, written on the surface, and eventually leaking back out. He later wrote an entire book about the struggle and called it the Black Hole War. Keep that war in the back of your mind. It does not end in this chapter. It ends with a clear winner and a famously conceded bet near the close of the night. For a few years, the holographic principle remained a beautiful and unsettling idea with no proof behind it, a hunch with a good argument attached. Compelling, but the kind of thing that could still turn out to be a mirage. And then, in 1997, a young physicist from Argentina rewrote the entire field in a single paper. His name is Juan Maldacena. He was born in Buenos Aires in 1968, took his doctorate at Princeton, and wrote his dissertation on, of all subjects, black holes in string theory, which is to say he had already spent years living inside the exact questions we have been circling all night. In late 1997, he published a paper with a forbidding title, The Large N-Limit of Superconformal Field Theories and Supergravity, and that paper has since become the single most cited work in the entire history of theoretical particle physics. More than 20,000 later papers have built on it. That number is abstract on its own, so let me frame it. Most physics papers, even genuinely good ones, are cited a few dozen times across their whole lifetime. A landmark paper might reach a few hundred. Maldacena's has been built upon more than 20,000 times, a number larger than the population of many towns. When it appeared, the field did not warm to it slowly and cautiously, the way it had resisted Bekenstein. It dropped everything and turned to face it. Within a year, 2 of the most respected physicists alive, Edward Witten, the only physicist ever to win the Fields Medal in mathematics, and a trio led by Stephen Gubser, had worked out how to actually use it, and the gold rush was on. Dwell for a second on how rare that is, because it tells you something. Physics does not usually move like that. Ideas normally creep in over decades, contested at every step, resisted and revised, the way Bekenstein's was. But every so often a result lands that is so plainly right, and so immediately useful, that the whole field reorganizes itself around it within months. People abandon problems they have chased for years and scramble to learn the new language as fast as they can, because they can feel the ground has shifted and they do not want to be caught standing on the old map. That is what happened in 1998, and the idea they all rush toward, the one that has shaped a full generation of theoretical physics since, was at its heart the claim that a universe can be a hologram, that the inside is written on the edge. Whatever else you carry out of tonight, hold on to this. It is not a fringe notion whispered at the margins. It has been sitting in the mainstream of physics for a quarter of a century. What Maldacena had found was the first concrete, fully calculable example in which the holographic principle is provably exactly true, not argued for, proven in a setting clean enough to check. He found 2 utterly different-looking descriptions of the same physics and demonstrated that they are, in fact, the same physics. We refer to the correspondence with a bit of alphabet soup, add E/CFT, but the idea beneath the letters is clean, and you do not need the mathematics to hold it. On one side of the dictionary, you have a particular kind of universe called anti-de Sitter space. Set the name aside. Picture it as a region of space with real gravity inside it, wrapped in a boundary at its outer edge, a little like the inside of an enormous bottle. Things fall in it. Things orbit. Black holes can form in it. It is a world with genuine depth, a true interior, all 3 dimensions of space doing their ordinary work. On the other side of the dictionary, you have only that boundary, the surface of the bottle, 1 dimension lower than the inside. And living on that surface is a completely different kind of theory, a quantum field theory of the sort that describes ordinary particles and forces jostling around, with no gravity in it whatsoever and no 3rd dimension of depth. Flat, in the sense that matters. Just fields humming on a surface, like ripples on the skin of a drum. That word in the middle of the alphabet soup, conformal, is hiding something beautiful, so let me unpack it. A conformal theory is one with no built-in sense of scale, no fixed length, no ruler stamped into it announcing how big things are supposed to be. You can zoom in or zoom out on it as far as you like, and it looks essentially the same, the way a perfect fractal does. And that turns out to be exactly the property you need for a dimension of depth to grow out of it. If the surface theory has no fixed scale of its own, then scale itself, how zoomed in you happen to be looking, is free to become a direction. The depth of Maldacena's universe is built out of the one thing the flat surface theory has to spare, its freedom to be looked at every magnification at once. And the dictionary is exact, entry by entry, not a vague family resemblance. Heat up the flat theory on the boundary, and a black hole appears in the interior. Cool it back down, and the black hole evaporates away. A particle sitting quietly deep in the bulk corresponds to a particular spread-out pattern of energy on the surface. The entire vocabulary of gravity, of falling and curving and orbiting, has a precise translation into the gravity-free language of the boundary, and physicists have spent nearly 30 years filling that dictionary in, word by word, checking entry against entry, and finding that it never once contradicts itself. That consistency, holding up across thousands of independent calculations by people who would have loved to break it, is most of why almost no one in the field doubts the correspondence is real, even in the absence of a complete mathematical proof. Maldacena's result was that these 2 descriptions are not merely similar, not loosely analogous. They are identical. Every single thing that happens in the 3-dimensional interior, with all of its gravity and depth and falling and orbiting, corresponds exactly to something happening in the flat, gravity-free quantum theory painted on the boundary. A star drifting through the interior is some specific pattern of activity on the surface. A black hole forming deep in the bulk is a hot plasma flaring up on the boundary. 2 languages, translatable word for word, describing one and the same reality. He had built the dictionary, and the dictionary was complete. Let that settle, because it is stranger than it first sounds. We are not talking about 2 theories that happen to agree, 2 different roads arriving at one destination. We are talking about one reality with 2 complete and equally valid descriptions, and neither of them is the more fundamental one. There is no hidden fact of the matter about whether the universe really has gravity and depth, The way the inside insists, or really is a flat quantum theory with no gravity at all, the way the boundary insists. Both are fully, exactly true at once. The depth is not an illusion painted over the real flat truth, and the flatness is not a trick hidden beneath the real deep truth. They are the same thing, and the question of which one is the genuine article simply dissolves in your hands. That is a genuinely new kind of answer for physics to offer, and it is the thing that lifts the word holographic out of metaphor and into mathematics. And here is the part that should stop your breath for a moment. In that dictionary, the third dimension itself, the depth of the interior, the very thing that makes it a spacious three-dimensional world instead of a flat sheet, is not fundamental. It is emergent. It is built out of the boundary theory. Distance into the interior, how deep into the bulk you go, corresponds on the flat side to something far more humble. Roughly, it corresponds to scale, to how zoomed in or zoomed out you are looking at the surface. There is an image that helps here. Imagine you had a map of a city at every possible level of zoom, a wide map of the whole city, a closer map of one district, a closer one of a single block, a street, a single doorway. Now stack all those maps on top of one another, the widest at the bottom, the most detailed at the top, and treat the height of the stack as a new direction in space. You have just built a third dimension out of nothing but a flat map, viewed at different magnifications. That, very loosely, is how the depth of Maldacena's universe is built out of the flat theory on its boundary. The dimension of depth is not a pre-existing stage. It is woven, layer by layer, out of the simpler thing on the surface, exactly the way the depth in a hologram is woven out of the flat interference pattern on the film. So when the interior insists that there is a third dimension of real space, the boundary description does not contain that dimension at all. It generates it. The depth is real, in the sense that everything living inside experiences it fully and completely, and could never tell it was generated. And the depth is derived, in the sense that the honest, total, leave nothing out description of the whole universe fits on a surface with one fewer dimension. Both of those are true at the same time. That is what it actually means for something to be a hologram. Not that it is fake, that its inside is the faithful readout of its edge. And here, by far the heaviest, the boundary comes to the center of the story. With Bekenstein, it was the skin of a single black hole. With Susskind, it was a haunting analogy and a density of bits. With Maldacena, it became a theorem. He had taken an entire universe, gravity and depth and orbiting stars and all, and proven in mathematics that other physicists could check and did check and have been checking for nearly 30 years, that the whole of it can be written down, with nothing left out and nothing lost, on its boundary. The surface is not a summary of the universe inside it. The surface is the universe, told in a different and more honest language. And this was never some idle abstraction that physicists admired in a frame and then walked past. The correspondence turned out to be a working tool, and that is the part that should make you take it seriously. Because the two sides are exactly equivalent. A problem that is impossibly hard on one side can be easy on the other. Physicists have used the gravity side of the dictionary to calculate the behavior of the quark gluon plasma, the searing, almost perfectly fluid state of matter that flashes into being for an instant when atomic nuclei are slammed together in colliders, a substance that is otherwise close to impossible to model. They have turned the dictionary on stubborn problems in the physics of exotic materials. It makes predictions. The predictions match the experiments. You do not get that from a metaphor. Metaphors do not predict the viscosity of a plasma. There was also a quieter triumph that closed the loop with everything in the last chapter. In 1996, just before Maldacena's paper landed, two physicists named Andrew Strominger and Kumrin Vafa pulled off something nobody had managed before. They counted. For a particular carefully chosen kind of black hole, they used string theory to count the actual hidden microscopic arrangements, the very things Bekenstein's entropy was supposed to be tallying, and they added them all up. The number they got matched the Bekenstein-Hawking formula exactly, 1/4 of the area, to the decimal. The hidden arrangements on the boundary were not a bookkeeping fiction after all. They were real, they were countable, and they sat precisely where the surface said they would. Now I have to be honest with you, because the honesty is the whole difference between this and a sermon. The universe Maldacena solved, that anti-de Sitter space, is not our universe. It has the wrong shape. Its gravity curves the wrong way, bending inward toward a neat boundary, where our universe appears to be doing the opposite, expanding outward, its galaxies flying apart a little faster every year, with no tidy boundary anyone has yet found to wrap a theory around. So what Maldacena strictly proved is that holography can be exactly, provably, true in a universe. He did not prove that it is true in this one. That gap is real, and an enormous amount of present-day research lives right inside it, trying to build a version of the dictionary that fits a universe shaped like ours. But do not let the gap shrink what was done, because what was done is staggering. For the whole of human history before this, the idea that our solid, three-dimensional world might be the projection of a flat surface would have been pure mysticism. A thing you mutter in a dorm room at 2 a.m. and feel slightly embarrassed about by breakfast. Maldacena dragged that idea into the one-room mysticism is not allowed to enter. He made it a calculation. He showed that there exists a real, self-consistent, fully worked-out universe in which the projection is not a figure of speech, but a proven mathematical fact, in which the inside genuinely is the readout of the boundary. The single open question, vast as it is now just whether we happen to live in a universe like that one. Which turns the whole long argument finally toward you. Because if the honest and complete description of a universe can live on its boundary, and the depth inside it is something that boundary generates rather than something that was simply always there, then we are forced to ask what that would mean for the depth you are lying inside right now, for the distance between your body and the ceiling, for the plain, obvious solidity of your own hand. If the boundary is the page, then what exactly does that make you? That is the question we walk into next. This is where the cosmic mathematics becomes personal. So let me bring it all the way down out of the equations and into the room you are lying in tonight. Everything I have described until now has been about universes, black holes, anti-de Sitter bottles, boundaries wrapped around the far edge of space, abstract, distant, safely out there. But the holographic principle does not stay out there, and that refusal to stay out there is the whole reason it disturbs the people who understand it best. If the honest description of a region of space lives on its boundary, and the depth inside that region is generated rather than fundamental, then the claim does not politely halt at the rim of a black hole. It is a claim about space itself, all of it. The space holding your body up off the surface beneath you, the space between your eyes and whatever they are resting on, the depth you have trusted. Without a flicker of doubt, every single second of your life. Hold on to the thing Maldacena's dictionary taught us, because it keeps people from misunderstanding this. The depth is not fake. I want to be careful with that word, because the lazy version of this idea is to say none of it is real. It is all an illusion. Nothing matters. That is not what the physics says, and it is a smaller, cheaper thought than the truth. The depth of the world is completely real, in the only sense that has ever mattered to you. You move through it. You reach across it. Light takes real time to cross it. Everything inside the projection experiences the projection fully and could never step outside to catch it being generated. And at the very same time, the depth is derived. The complete and honest account of it might be written on a surface that has one fewer dimension than the world you feel. Real and derived, both at once. That is not a contradiction. That is what it is to live inside a hologram. Now, let me make the most personal version of this as concrete as I can, with a number. We met the Bekenstein bound at the very start of the night. The rule that the most information any region can hold is set by its boundary. Bekenstein wrote down the universal form of that bound in 1981, and here is what it says about you. The amount of information needed to describe a human being completely, perfectly, down to the position and state of every last particle, is finite, not unimaginably large and then trailing off into infinity. Finite, a specific, countable number of bits. For a region of space about the size of a human brain, that number comes out to around 10 to the 42nd bits. Let me try to set that somewhere you can stand next to it. A good modern laptop might store a few trillion bits, something like 10 to the 12th. The information it would take to specify a human brain to the quantum level is larger than that by a factor with 30 zeros in it. So you are vast. You are a quantity of information so large that every computer our species has ever built, stacked together, could not hold a single one of you at full resolution. But vast is not the word that should stay with you. Finite is the word that should stay with you. Because for the whole of human history, we have reached for infinity whenever we wanted to describe the soul, the self, the inner life. Bottomless, boundless, beyond measure. And the holographic principle quietly disagrees. It says there is a number, a real, finite number of yes or no answers that would capture you entirely, with nothing left over. You could, in principle, be written down. And if Bekenstein and Suskind and Maldacena are right about where information lives, then the place you could be written down is not a vast interior volume at all. It is a surface. There is a second consequence, and it is just as strange once you sit with it. The world has a finite resolution. There is a bottom to it. You are used to the idea that you can always look closer. Take any object and imagine a powerful enough microscope, and you expect to keep finding more detail, smaller and smaller, forever, with no end. The world feels infinitely fine-grained, the way a number line feels like it can always be cut in half again. The holographic principle says no. There is a smallest meaningful scale, the Planck length we met earlier, and below it the question, what is happening here, stops having an answer. There is no finer detail to find. The region simply cannot hold any more distinctions because its boundary cannot carry any more bits. Think of it the way a digital photograph works. From a distance, the image looks perfectly smooth, with gradients of color flowing into one another. But zoom in far enough, and you hit the pixels. The image has a finite resolution. There is a last level of detail, and beneath it there is nothing more to see, because there is nothing more stored. The holographic principle is saying, very seriously and with hard mathematics behind it, that reality is like this. Not infinitely detailed, pixelated in the deepest sense, at a scale so fine you will never reach it, but real and final. Zoom in far enough on anything, and the universe runs out of answers, because the boundary has run out of room to write them. And this applies to everything, all the way up. The entire observable universe, the whole sphere of everything we could ever see, has a finite information capacity too. The number is something like 10 to the 120th bits. Enormous beyond any feeling, yes, but finite. There is a largest possible story the universe could be telling about itself, a longest possible book, and it has a definite length. The cosmos is not an infinite reservoir of detail. It is a finite quantity of information, and that quantity is set in the end by surfaces. Now I have to stop and draw a hard line, because this is exactly the point where people take a wrong turn, and I do not want you taking it. When you hear that reality is information, that depth is a projection, that the world is pixelated and could be written down, there is an obvious place the mind wants to run. It wants to say, so we are living in a simulation. We are inside a computer. Someone, somewhere, is running us. That is not what the holographic principle says, and the difference is not a small one. A simulation needs a simulator. It needs hardware somewhere outside, a machine, a programmer, a civilization that booted us up and could shut us down. The simulation idea is a claim about something beyond our universe looking in. What we have been building toward is the opposite. It is a claim about how this universe, all on its own, with nothing outside it, stores and expresses its own information on its own boundary. There is no programmer here. There is no outside computer. There is no one running you. There is only the universe, describing itself completely on its own edge, the way a hologram describes its image, completely on its own film, with no projector hiding in another room. So when someone tells you that physics has proven we live in a simulation and points at the holographic principle to do it, they have quietly swapped one idea for another. One is a serious result in theoretical physics, built on black hole entropy and a dictionary that makes testable predictions. The other is a philosophical argument about probability and hypothetical future civilizations, and it is a separate conversation for a separate night. Reality being written on a surface does not mean reality is running on a machine. Hold those apart, and you will understand this better than most people who talk about it confidently. So set the simulation aside and stay with the stranger and more beautiful thing the physics actually says. Here is the picture, brought all the way home. You are a pattern, a finite, enormous arrangement of information, and the honest, complete account of that pattern may not live in the warm, three-dimensional volume of your body, where you have always assumed you live. It may live on a boundary, a surface, and the depth you feel, the inside of you, the sense of occupying a roomy private space behind your eyes would be the readout, the image, the thing the surface generates. And being a pattern is not the thin, diminished thing it sounds like at first. Consider that almost none of the actual matter in you tonight was part of you a decade ago. The atoms cycle through, breath by breath and meal by meal, swapped out and carried off and replaced, and still you persist. You are not the atoms. You never were. You are the arrangement they are holding for a while, the pattern they are briefly carrying, the shape that stays itself while the material pours through it like water through the standing wave that hangs in a river over a rock. The wave is real. You can see it, point to it, photograph it, and not one drop of water stays inside it for longer than an instant. And that changes where you live. A lump of matter has to be somewhere in particular. Information does not. Information, this entire night, has been quietly insisting, finds its truest home not inside a volume, but across a surface. To say the real you might be written on a boundary is not to exile you to some cold and distant wall. It is to say that a pattern has finally been handed the kind of address a pattern was always meant to have. Now the boundary comes forward again, and this time it is about you, not a black hole or a distant bottle of space. Lie still for a moment and feel the depth of yourself, the space your breath moves through, the distance from the back of your skull to the front of your eyes, the solidity of your own weight pressing down. Every part of that, the holographic principle suggests, could be the faithful projection of information arranged on a surface you cannot point to and will never see. In the same way, the floating, three-dimensional image of a hologram is the faithful projection of a flat pattern etched on film. I find that I cannot decide whether this is the loneliest idea in physics or the most intimate one, and I have gone back and forth on it for a long time. There is a version of it that feels like exile, the sense that the solid inner world you trusted was always somewhere else, written on a wall at the edge of everything. And there is a version that feels like the opposite, a strange closeness, the idea that nothing about you is lost in a bottomless interior, that you are written down somewhere, completely, every bit of you, held on a surface that does not forget. I think both readings are honest. I think the idea is large enough to hold both, and that you get to choose most nights which one you carry. But there is one enormous and honest gap left in all of this, and I promised you I would not paper over it. We have a boundary for Maldacena's bottle universe. It sits at the outer edge of that anti-D sitter space, neat and well-defined. We do not have a boundary like that for our own universe. Ours is not a bottle. Ours is expanding, flying apart, its galaxies racing away from one another faster every year, with no tidy wall at the edge for a theory to hang on. So if our universe is a hologram, the obvious and haunting question is, where is the film? Where is the surface that we are the projection of? Nobody knows. There is a leading candidate though, unproven but hard to forget once you hear it. It is called the cosmological horizon, because the universe has a finite age and light has a finite speed. There is a limit to how far we can ever see in any direction, a vast sphere centered on us, beyond which the light has simply not had time to reach us. That sphere, that horizon at the very edge of the observable, behaves in some of the same suggestive ways a black hole's horizon does. It has an area. It seems to have an entropy. And some physicists suspect that everything inside it, every galaxy, every star, this room, you, might be the readout of information encoded on that impossibly distant surface, the boundary of the seeable world, wrapped around us at a radius of billions of light years. There is a vertigo hidden in that idea worth sitting with. If our boundary is the cosmological horizon, the far sphere of all we can see, then notice who sits at the center of it. You do. So does every other observer, everywhere, each one at the center of their own sphere of the visible, each with their own horizon drawn at their own arm's length from the edge of time. There is no single privileged surface that the whole universe is painted on. There is a different horizon for every vantage point in existence, and somehow they would all have to be telling one consistent story. The page, if there is a page, is not one page. It is redrawn around every observer who looks, and the question of how all those pages could possibly agree is one of the genuine puzzles physicists are chewing on at this very moment. It also gives a sharper edge to that staggering number from before, the 10 to the 120th bits the whole observable universe can hold. That is not a piece of fun cosmic trivia. If the holographic principle holds, it is a hard ceiling. It is the total length of the story the cosmos is able to tell about itself. Every particle, every position, every possible arrangement of everything, bounded by the area of the horizon around us. Reality is not an infinite book. It is a very, very long one with a final page, and the binding is a surface at the edge of sight. Sit with the shape of that, even though it is only a candidate. It would mean the surface you are written on is not above you or below you or in any direction you could point. It would be the sky, the farthest sky there is, in every direction at once, the edge of how far light has traveled since the beginning. The page you are printed on would be the horizon of everything. But I have to keep the books honest. That is a suspicion, not a theorem. Maldacena proved the projection is exactly true in a universe with the wrong shape for ours, and the work of building a real, rigorous version for an expanding universe like the one we actually live in is unfinished and hard and ongoing right now in offices full of chalkboards. What we have is a proof of principle so strong it cannot be ignored, a fistful of suggestive hints that it applies to us, and a boundary we have not been able to find or pin down. That is the genuine state of it tonight, not certainty, something rarer and more interesting than certainty, a door that has been opened, with the far side still in shadow. And there is a deeper layer underneath even this, one that most retellings of the holographic principle never reach. Because so far I have spoken as though space is a stage and information is painted on its boundary. But a handful of physicists working in the last 15 years have started to suspect something more radical still. That space is not a stage at all, that the 3 dimensions you move through are not a container that information sits inside, but are themselves woven, stitched together out of something more fundamental. And the thread they are woven from is the strangest substance in all of quantum mechanics. We go there next. The strangest thing in quantum mechanics is not really a thing at all. It is a relationship. It is called entanglement, and Albert Einstein disliked it so intensely that he spent the last decades of his life trying to prove it could not be real. Entanglement works like this. You can prepare 2 particles together in such a way that their fates are linked, and then carry them apart, across a room, across a country, in principle across a galaxy. Measure one, and you instantly know something about the other, no matter how far away it has gone. They behave like a single system that space has failed to separate. Einstein called it spooky action at a distance, and he meant the word spooky as an insult. He was sure it pointed to a flaw in the theory. He was wrong. Experiment after experiment, growing more careful and more airtight every decade, has shown that entanglement is exactly as real and as strange as the mathematics says. The universe genuinely stitches distant things together in a way that does not care about the space between them. For most of the last century, entanglement was filed away as a curiosity of the very small, a puzzle for philosophers and a tool for building quantum computers. And then, in 2010, a physicist at the University of British Columbia named Mark van Riemsdonk asked a question about it that almost no one had thought to ask. And the answer he found was so unsettling that the first journal he sent it to is said to have turned it away. It later won a prize for being one of the most important short ideas in physics that year. The idea was this: what if entanglement is not something that happens inside space? What if entanglement is what makes space? Here is the thought experiment that led him there. Go back to Maldacena's dictionary, the universe in a bottle, and the flat theory on its boundary. Van Riemsdonk took the boundary theory and imagined slowly dialing down the entanglement between two halves of it, just turning the connection down, like a dimmer switch. And he watched what happened to the three-dimensional space inside the bottle, the space that the boundary generates. What happened was that the interior began to come apart. As he reduced the entanglement between the two halves of the boundary, the region of space connecting the corresponding two halves of the interior stretched and thinned and pinched like a bridge of taffy being pulled from both ends. And when he turned the entanglement all the way down to nothing, the bridge snapped. The interior split into two separate pieces of space, no longer connected at all, infinitely far apart. The space between them did not just grow, it ceased to exist. Sit with what that means, because it inverts everything. We think of space as the stage, the empty container that exists first, and then things move around inside it and occasionally get entangled. Van Riemsdonk's result says it is the other way around. The entanglement comes first. The space is the consequence. Two regions are near each other because they are heavily entangled, and far apart because they are only weakly entangled. And what we experience as distance, as the smooth fabric of space holding the world together, is really a map of how entangled everything is. Pull out the entanglement and there is no space left over. There is no empty stage underneath. The stage was woven from the threads the whole time. Another physicist, Brian Swingle, had been circling the same insight from the direction of quantum computing. He noticed that the particular way information is entangled in these boundary theories has a structure, a kind of branching network of connections, and that the shape of that network of entanglement matches, almost exactly, the shape of the curved space it produces in the interior. The architecture of the entanglement is the architecture of the space. The scaffold and the building are the same object, seen two ways. Space, in this picture, is something like frozen, structured entanglement, and gravity is what that frozen structure does when you lean on it. For a few years, this stayed a gorgeous picture without a precise rule under it. Then, in 2006, two physicists named Shinsei Ryu and Tadashi Takayanagi found the rule, and it is one of the most quietly stunning results in the whole story. They proved, inside Maldacena's setting, that you can take any patch of the boundary, measure exactly how entangled it is with everything else, and that number equals the area of a particular surface reaching into the interior, divided by 4. Divided by 4. The very same 1/4, the very same area law that Bekenstein and Hawking had stumbled onto at the horizon of a black hole 30 years before. Sit with that, because it is not a coincidence, and it is not a metaphor. The amount of entanglement on the surface is, on the nose, the area of a surface in the space that entanglement generates. Entanglement and geometry are not two things that resemble each other. They are one quantity, written in two alphabets. The threads do not merely hold space together in some loose, poetic way. The number of the threads is the size of the space. When Van Ramsdonk dialed the entanglement down and watched the bridge of space thin and snap, Ryu and Takayanagi had handed him the exact equation for how thin and when. The fabric of space had been turned into arithmetic. But before we follow that thread to where it leads, I have to tell you about the moment it nearly burned the whole picture to the ground. Because in 2012, 4 physicists found a paradox so sharp that it set the field at war with itself for years, and it carries a name that sounds like it belongs in a different kind of story: the firewall. Here is the trap they laid, and the unnerving thing is that it is built entirely out of pieces we have already set down. Remember that for information to escape a black hole, as Hawking finally conceded it must, the radiation leaking out has to be deeply entangled with the radiation that left earlier. That entanglement is the very mechanism by which the information gets smuggled out, scrambled across the whole long stream of escaping particles. Hold that. Now remember the other thing. The equivalence principle, the cornerstone Einstein built general relativity on, says that falling through the horizon of a large black hole should feel like nothing at all. No wall, no edge, no drama. Empty space is empty space, and crossing the horizon ought to be as gentle as crossing any other patch of nothing in the dark. But for the horizon to feel like ordinary empty space, each particle just outside it has to be entangled with its partner just inside. That is simply what empty space is, down at the quantum level. A fine web of short-range entanglement stitched across every point, including the points along the horizon. And here is the knife. Quantum mechanics has a rule as strict as anything in physics. Entanglement is monogamous. A thing can be fully entangled with one partner, or share itself thinly among many, but it cannot be completely entangled with 2 separate partners at once. So a single escaping Hawking particle is being asked to do the impossible. To carry information out, it must be entangled with the early radiation far away across space. To keep the horizon smooth and empty and survivable, it must be entangled with its partner just inside the hole. It cannot be both. One of those demands has to break. The 4 physicists, known ever since by their initials as AMPS, followed the logic to its blunt end. They argued that what breaks is the horizon, the entanglement with the interior tiers, and tearing entanglement, like snapping any taut bond, releases energy, an enormous amount of it. They calculated that an old black hole, one that had already radiated away more than half of itself, would be wrapped not in gentle empty space, but in a seething shell of high-energy particles. A firewall. An astronaut falling toward it would not drift peacefully inward toward whatever waits at the center. They would be burned to nothing the instant they touched the edge. Take in what that conclusion would cost, because it is not a small bill. It would force a choice between the 2 deepest theories we have. Either information really is destroyed inside a black hole after all, and quantum mechanics is broken at its root, or the horizon is a wall of fire, and Einstein's equivalence principle, the idea that gave us gravity itself, is broken instead. The 2 pillars this entire night has been balanced on, turned and pointed at each other, and each one demanded that the other fall. For several years, some of the finest minds alive stared at the firewall and could not find the way out. A few of them came to think it might simply be true, and that falling into a black hole really does end at a wall of fire. Not everyone accepted the wall, and the pushback was ingenious. One of the sharpest replies came from two physicists, Daniel Harlow and Patrick Hayden, who pointed out something almost slippery. To actually trigger the contradiction, an observer would first have to perform a measurement on the escaped radiation, so monstrously complicated that completing it would take longer than the black hole has left to live. The paradox might be ironclad on paper and still be impossible to ever stage in reality, shielded from happening by the sheer computational labor it would demand. That is a strange and very modern flavor of resolution. The idea that nature might be protected from contradicting itself, not by a law forbidding it, but by the contradiction being too much work to ever assemble. The argument that started there has not fully settled even now, more than a decade on. The escape, when it finally came, was so audacious that it loops us straight back to the thread we were following, and to two names we already know. In 2013, Juan Maldacena and Leonard Susskind, the man who built the dictionary and the man who fought the Black Hole War, wrote a paper together proposing something they summed up in a tiny equation that looks like a typo: ER equals EPR. To understand why that line is so audacious, you have to know that both halves of it come from the same year, 1935, and from the same man, Einstein. In 1935, Einstein and Nathan Rosen wrote a paper describing what we now call a wormhole, a bridge through space-time connecting two distant points, a shortcut tunneling from here to there. The initials of that paper, Einstein and Rosen, are E and R. Also in 1935, Einstein, with Boris Podolsky and Nathan Rosen, wrote a completely separate paper, the one introducing the spooky entanglement he was trying to discredit. The initials of that one are E, P, and R. For 78 years, those were two unrelated papers about two unrelated ideas. Wormholes over here, entanglement over there. Maldacena and Susskind proposed that they are the same idea, that two entangled particles are connected by a wormhole, a tiny, untraversable bridge of space. That entanglement simply is a wormhole, viewed up close, which means that when you entangle two things, you are not just correlating them. You are building a thread of space between them. You are sewing. And this is what quietly puts out the firewall. Go back to the trapped Hawking particle, asked to be entangled with two partners at once, the one inside and the early radiation far outside. If entanglement is a wormhole, then those are not two separate partners after all. The particle inside and the radiation outside are joined through a tiny bridge of space, which makes them, in a sense, the same partner reached by two routes. The monogamy rule was never violated. There was only ever one partner wearing the disguise of distance. The horizon stays smooth. The astronaut falls through unburned, and information still escapes because the wormhole carries it. The paradox dissolves the moment you accept that the threads of entanglement are themselves threads of space. Think about Einstein in this. The man wrote down wormholes and entanglement in the same year, hated one of them, and went to his grave never suspecting they were two descriptions of a single thing. It took the better part of a century and the long road through black hole entropy and Maldacena's dictionary before anyone could see that the spooky action he despised was all along the very fabric of the space he loved. I do not know a cleaner example of how long an idea can hide inside the things we already know. I have to keep this honest, the way I have all night. ER equals EPR is a conjecture, not a proven theorem. It has been worked out in idealized, simplified settings, the same anti-de Sitter bottles, the same eternal black holes, and it has thoughtful critics who are not convinced it survives contact with a realistic universe. The entanglement builds space story is supported by beautiful mathematics and almost no direct experiment. This is the living edge of physics, where the ground is genuinely soft, and I would be lying to you if I pretended otherwise. But the direction it points is unmistakable. And it is the same direction everything else in this story points. Toward the inside being made of the outside. Toward depth being woven from something flatter and more fundamental. There is one physicist who has pushed this further than almost anyone, and his name is Eric Verlinde. If space is emergent, woven from information and entanglement, then Verlinde asked the obvious and reckless follow-up. What about gravity? Gravity, after Einstein, is nothing but the bending of space. So if space itself is not fundamental, then gravity, the bending of a thing that is not fundamental, cannot be fundamental either. It must be emergent too. In 2010, in a paper on the origin of gravity, Verlinde argued exactly that. Gravity, he proposed, is not a basic force of nature like the others. It is an entropic force. It is a statistical tendency, the same kind of thing as the pressure of a gas or the pull of a stretched rubber band, both of which are not fundamental forces at all, but the bulk result of countless tiny arrangements seeking their most probable state. Verlinde claimed he could start from information spread across holographic surfaces, apply nothing but thermodynamics, and derive Newton's law of gravity out the other side. The apple falls in this picture not because space tells it to, but because the universe is drifting toward its most likely arrangement of information, and a fallen apple is part of a more probable world than a hanging one. In 2016, he went further still and tried to show that this emergent gravity, worked out carefully, would naturally produce the strange extra pull that astronomers see at the edges of galaxies, the pull we normally explain by inventing invisible dark matter. If Verlinde were right, there would be no dark matter particle to find, only gravity behaving the way emergent gravity must. To feel what an entropic force even is, picture a single long molecule, a strand of rubber, jiggling in warm water. Stretch it straight and let it go, and it snaps back into a tangled coil. It feels as though something pulled it, but nothing did, not in the ordinary sense. There is no spring hidden inside it, no force reaching out to yank it back. The molecule coils because there are vastly more tangled, jumbled shapes available to it than straight ones, and the ceaseless random jiggling simply finds its way, overwhelmingly, into the more numerous state. The pull you feel is statistics wearing the mask of a force. Verlinde's audacious claim is that gravity, the most familiar force there is, the one holding you against your bed at this very moment, is the same kind of illusion. Not a fundamental pull, but the universe drifting toward its most probable arrangement of information on its holographic screens. And that drift, felt from the inside, is the thing we have always called weight. And here I have to put the warning label on clearly, because this is the most contested idea in the whole night. Verlinde's emergent gravity is not accepted physics. It is a bold, beautiful, and deeply disputed proposal. Many physicists think the derivation hides its assumptions, and the astronomical tests of his dark matter claim have come back mixed at best. with some observations fitting and others flatly refusing to. I am telling you about it not because it is true, but because it shows you how far serious people are willing to follow this thread. If space is information on a boundary, then someone was always going to stand up and say that gravity is too, and Verlinde did. Whether the universe agrees with him is still being fought over. So far, this has all been theory, mathematics, an argument, however gorgeous. You would be right to want something measured, something the universe itself was asked, out loud, with an instrument, and in 2017, it got asked. A team of physicists, led by Niayesh Afshordi and Costa Skendris and their collaborators, published a paper in Physical Review Letters with a title I love, From Planck Data to Planck Era. They built holographic models of the infant universe, models in which the earliest moments of everything are described not by ordinary three-dimensional space unfolding, but by a lower dimensional theory living on a kind of boundary, the holographic idea applied to the birth of the cosmos. And then they did the thing that separates physics from philosophy. They compared their holographic models against real data, against the cosmic microwave background. The version of holography they leaned on, developed over the previous decade mostly by Costa Skendris and his collaborator Paul McFadden, does something dizzying with the boundary. In Maldacena's original dictionary, the boundary is a surface somewhere out in space. Here, the boundary is a moment in time. The entire three-dimensional expanding infant universe gets described by a simpler theory with no gravity and one fewer dimension. A theory that sits, in effect, right at the beginning of everything. The expansion of the cosmos, the unfolding of space itself, becomes in this language exactly the kind of emergent thing that depth was inside the bottle universe. Time, or at least the swelling of space through time, gets generated out of a flat theory that does not contain it. The whole history of the early universe, read off a surface at the dawn of it. The cosmic microwave background is the oldest light there is, the faint afterglow of the Big Bang, released about 380,000 years after the beginning, when the universe first cooled enough to become transparent. We have mapped it across the whole sky with extraordinary precision, every faint, hot and cold speckle in it. It is the most detailed photograph of the early universe we will ever have, and any theory of how the cosmos began has to match its pattern or die. When Afshordi and Skendris and their team checked their holographic models against that map, the models did not die. They fit the data about as well as the standard model of cosmology does, the conventional picture built on inflation and ordinary expanding space, competitive across most of the pattern in that ancient light. Now let me be scrupulous, because the result has been overstated by excited headlines ever since. The standard model still does a little better overall, especially at the very largest scales on the sky. And this was a test of the early universe, not a measurement showing that you, tonight, are a hologram. It did not prove the holographic idea. What it did was far rarer and quieter than proof. It showed that a model in which the universe is fundamentally holographic can stand toe-to-toe with our best conventional cosmology against real data and not lose. For an idea this radical, surviving its first serious encounter with observation is no small thing. Which brings us finally back to a war I promised you we would finish. The Black Hole War between Leonard Susskind and Stephen Hawking over whether a black hole destroys the information that falls in. For decades, Hawking said it does, and quantum mechanics must simply accept the loss. Susskind and at Hooft, and a growing crowd behind them said it cannot, that the information must survive on the boundary and leak back out. For a long time it was a standoff, two camps, and no way to settle it. In 1997, the disagreement became a formal bet. Hawking, together with the physicist Kip Thorne, wagered against John Preskill that information truly is destroyed inside a black hole, gone for good. The stake was almost comically modest for a question about the foundations of reality. The loser would buy the winner an encyclopedia, a reference book, from which, as the bet wryly put it, information can be recovered at will. For 7 years it sat unresolved. And then in 2004, at a physics conference in Dublin, Stephen Hawking stood up in front of the world's press and conceded. He had changed his mind. The weight of evidence, much of it flowing from Maldacena's dictionary and the holographic principle, had convinced him that information is not destroyed after all, that it is preserved, scrambled across the horizon, written on the boundary, and ultimately carried back out in the radiation. He handed John Preskill a thick encyclopedia of baseball, of all things, and admitted he had been wrong for 30 years. Susskind had won the black hole war. The information lived on the surface, exactly as the holographic principle demanded. But even that was not quite the end, because conceding a bet is not the same as showing precisely how the trick works. The deepest version of the puzzle held out for another 15 years. If information really does escape a black hole, then the disorder of the radiation coming off it should follow a very particular path over time, rising for a while and then falling back down, a shape physicists call the Page curve. Hawking's original 1975 calculation gave the wrong shape, a disorder that only ever climbs, which is exactly what destroyed information would look like. Nobody could find a calculation in the same style that gave the right curve, until in 2019, several groups did. Using new tools with roots in the holographic ideas, they found a way to redo the calculation that produces the Page curve correctly, the rising and then falling shape that means the information comes out. The math finally agreed with the conclusion Hawking had conceded on a stage in Dublin. The information was on the boundary the whole time. The mechanism they uncovered carries a name almost as evocative as the firewall: islands. When they redid the calculation with real care, they found that past the halfway point in a black hole's life, the region you must count as belonging to the outside radiation suddenly swallows a piece of the deep interior, an island of inside that turns out to be secretly part of the outside, joined to it through exactly the entanglement as wormhole logic that ER equals EPR had pointed at. After a certain age, the inside of the black hole is no longer cleanly inside. In the only bookkeeping that actually governs where the information is, the interior has quietly become part of the surface, which is the holographic principle stated one final time, now in the language of the most demanding calculation anyone has pulled off. The inside was the boundary all along. There is a reason some of the very best physicists alive have poured whole careers into this, beyond the sheer strangeness of it, and it deserves naming before we gather the threads. For 100 years, physics has been split down the middle by a single problem it cannot solve. We have quantum mechanics, which governs the very small with ruthless precision, and we have general relativity, which governs gravity and the very large with equal precision, and the two flatly refuse to be married. Try to force them together, and the mathematics spits back infinities, nonsense, blank walls. Every attempt to build one theory underneath both of them has broken on this rock. And the holographic principle is the most promising bridge anyone has found across that chasm in 50 years. Because in Maldacena's dictionary, a world with gravity on one side equals a world without gravity on the other. Holography quietly performs the impossible trick. It writes gravity in the plain language of ordinary quantum mechanics. It is, at this moment, our single best hope of finally learning what space-time is actually made of. That is why none of this is a sideshow. It may turn out to be the doorway to the deepest unsolved problem in all of science. So step back and look at what has actually converged here, because it is easy to lose in the details. We have a principle born at the edge of a black hole that the contents of a region are written on its boundary. We have a theorem, Maldacena's, proving that an entire universe can be exactly described by its surface. We have a deeper layer suggesting that space itself, and maybe gravity, is woven out of the entanglement living on that surface. We have a first observational test against the oldest light in the sky, that the holographic idea survived. And we have the most famous paradox in modern physics, the question of whether the universe can destroy information resolved in favor of the boundary with a conceded bet and a calculation to back it up. That is why, when someone says reality might be a projection, the right response is not a smirk. It is not mysticism, and it is not a metaphor someone reached for to sound profound at a party. It is the place a chain of hard, checkable, often grudging physics has been pointing for 50 years, from Bekenstein's stubbornness to Hawking's surrender. The surface is not hiding the universe. The surface, more and more, looks like where the universe is actually kept. Which leaves only the last question, the one we started with, and the one you will carry out of here tonight. If the deepest, truest description of the world is written on a boundary, and the depth and solidity you live inside is the readout, then what exactly are you? Let me try to answer that gently, because it is time to bring this all the way down to the quiet and to you. For your whole life, without ever once choosing to, you have believed a single simple thing about yourself: that you are in here, that there is a solid, three-dimensional you, filling a small private volume of space somewhere behind your eyes and inside your skin, depth all the way down, a real interior, with you tucked somewhere safely within it. It is the most natural belief a person can hold, and until tonight, you never had the smallest reason to question it. Tonight gives you a reason, not a certainty. I have been careful all the way through not to hand you a certainty, because the honest physics does not have one to give. But a reason, yes, a real one, built out of black hole entropy and a dictionary that makes predictions and the oldest light in the sky. And the reason says, quietly, that the inside you have always assumed you live in may not be where you live at all. Go back to where we began, to the picture everyone carries. Volume is the container. The world is a vast three-dimensional space, and things sit inside it. And the bigger the inside, the more it can hold. That was the belief, and it was the considered conclusion of a century of good science, and we watched it crack, beginning at the one place in the universe that refused to obey it. A black hole keeps its contents on its surface, and then the crack ran outward through de Hooft and Susskind and Maldacena until it had spread, at least in principle, to all of space, to this room, to you. So here is the reframe, and I want to lay it down softly, because it is a strange thing to be told as you are getting ready to sleep. You may not be a solid object in a deep world. You may be a pattern, a vast, finite, exquisitely detailed pattern of information, and the truest home of that pattern may be a surface, a boundary, and the depth you feel right now, the roominess of your own body, the distance from your chest to the ceiling, the solid weight of you against the bed, may all be the readout, the image the surface is throwing, the 3 dimensions you live in, generated faithfully from a description that has 1 dimension fewer. I know how that can land. There is a version of this that feels like the loneliest sentence ever spoken, that the real you was always elsewhere, flattened onto some wall at the edge of everything, and that the warm interior you have lived inside your whole life is only a projection, only an image, only light. If that is the version that reaches you tonight, set it down. It is not the only honest reading, and I do not think it is the truest one. Because remember what a hologram actually is. The floating, 3-dimensional image is not a lie told by the flat film. It is not less real than the film. It is what the film is for. The image is the film, expressing everything it holds. And if you are the image, then you are not a thin or a lesser thing. You are the full and faithful expression of every bit of information that makes you what you are. Nothing left out, nothing lost. And there is something almost tender hidden in that once you stop flinching from it. For your whole life, you have half believed that the deepest parts of you are bottomless, that they trail off somewhere inside into a private dark that nothing could ever fully reach or hold. The holographic principle says the opposite. It says you are finite and complete and written down. Every memory, every version of you, every small, unrepeatable detail held on a surface at a density so fine you will never see the grain of it, not scattered through an interior that forgets, held on a boundary that does not. So let the old picture loosen, just for tonight. You do not have to decide anything. You do not have to believe the universe is a hologram, and the physicists who study it for a living would tell you not to. Not yet. Not until the boundary of our own expanding universe is found and the dictionary is rewritten for a cosmos shaped like ours. The honest state of it is a door standing open, with the far side still in shadow. That is all. But it is enough to lie inside differently for one night. Feel the depth of yourself, the way you always have. The breath going down into you and rising back. The quiet space behind your eyes, where the day is finally going still. The weight of your body settling into the dark. None of it is taken from you by any of this. It is all exactly as real as it has ever been. It is simply, perhaps, written somewhere you cannot point to. Read out, faithfully, from an edge at the far rim of everything there is. One last time the boundary comes forward tonight, and it is the gentlest. It began as the skin of a black hole, a place of terror and crushing and no return. It became a theorem, a surface a whole universe could be written on. And it ends here, as something almost intimate. The page you were printed on, the edge that holds you, completely, and does not let a single bit of you fall through. And if it unsettles you, this thought of being written somewhere you cannot see, turn it over once more before you sleep. A photograph is only ink or light on a flat surface, with no depth in it at all, and yet it can hold a face you love completely enough to make your chest ache across a lifetime. The flatness takes nothing from the face. A song is only a thin pattern of pressure in the air, gone the instant it is played, and it can still carry everything a person felt the year they first heard it. The surface was never the enemy of the depth. The surface is how the depth gets kept. You spent your whole life believing you were hidden somewhere deep inside. Let yourself consider, as you drift off, that you were never hidden at all, that you are spelled out in full, on the surface of everything, in light that does not forget, and that the depth you are sinking into right now, soft and dark and yours, is simply the universe doing the only thing it has ever done, reading you back to yourself, from the edge, one bit at a time. The surface has you. It always did.